Cool. Well, whilst you're getting set up, Gabe, I'll just welcome everybody to this month's developer forum. You've already got the title slide here, so we can see what the topic is. But yeah, this week we're going to be getting a presentation on ALTREP, which from my history lesson and digging around has actually been in R since R 3.5, which is end of 2017. So it's been around and available for a while, but this was by far and away the kind of runaway winner in our little poll of topics people wanted to discuss in these sessions. So I guess it's something that we're all aware of, but perhaps unfamiliar with, which presumably is why it came in that kind of position. So hopefully we've got exactly the right guys we need to teach us about this. So Gabe, and I can see Luke is also on the call now. So the floor is yours, Gabe.
Great. Yeah, so first off, thanks for the invitation. Thanks everyone for being interested. I'm pretty proud of ALTREP, of the work that I did with Luke to help put this in, and I hope that it's actually going to be useful to sort of developers like you guys, because that is the ultimate goal, is to make something that's going to be useful. And so with that, I'm going to go ahead and get started. I've got a number of slides that will go through sort of the why and how and basic what of what ALTREP is, and then depending on timing, I threw together a little example ALTREP package that's also available on GitHub, and I posted it in the Slack. So either if we have time, I'll go through some of that in this hour, and if not, you can go ahead and look at that afterwards. That's publicly available. It'll be staying up after. So before we get started about how the ALTREP works, we're going to talk a little bit about why the ALTREP exists at all. So if you can imagine, it's actually 3.4, I believe, when it was first went in, but not very much of it went in, and then it's been incrementally increased since then. But if you think back to the year of R 3.3 or so, I was sitting in my office, because I had an office back then. I wasn't in my bedroom, and I was thinking to myself, what does R need? What do the R internals need? And obviously they needed more complexity, because if anyone was working in R at the time, they knew that the RC API was known for being very simple and easy to work with. But there's a reason that we added this extra complexity, and it's largely twofold. So first off, we need to talk a little bit about how R viewed a vector in C underneath the R code that you're generally going to be running, but down in the C where the internals are implemented. So there are two basic primary pieces to this. The first is the header, which carries around things like how long the object is, what type it is, whether it's an integer vector or a raw vector, a character vector, or what have you, and various other info that's not going to be super relevant to our discussions here. And the second is the payload. That's the actual values that make up the vector that you think of when you have a vector in R. And that's just the values, because all of the sort of metadata, all of the information about what type of object it was all in the header, right? And the thing to know about that is that at the time, back then, these were tightly coupled together. And what that means is that the header and then the payload were contiguous in memory. You had a one block in memory that was the header, and then immediately after that was the first value of the payload. And there was no flexibility about that at all. And that does actually give you efficiency benefits, because walking along a pointer in C code is extremely, extremely fast, but it's also very restricted. And the other thing is, not only did the payload have to be contiguous directly after the header, but it also had to be in the simple array format. So if you have an integer vector, then it had to be an int array. It couldn't be anything else, no matter what you knew about the structure of your data or anything like that. It was always a simple integer array that came directly after the header. Okay. So that's one of the primary sort of motivations, and we'll talk about why we may have wanted to, relax that in a bit. And the other one is when are copies data. So I'm going to give you just a very brief and incomplete rundown of when duplication was triggered in terms of vectors mostly. So R has always been what we call copy on write, which means that it behaves as if every time you assign a value, a vector to a new variable or pass it to a function, it duplicates the data. It behaves that way. You would not be able to tell the difference between how R operates and if it actually was doing that copying, except for how fast it was. But it doesn't actually do those duplications unless it needs to, right? And the way that it gets away with this is by realizing that, you can have as many pointers as you want to data. As long as it doesn't change, they can all share it. But as soon as one of the variables that's pointing to this shared object changes one of the elements, so you use bracket to assign, a new value into one of your elements, then suddenly it's not shared anymore. It's different than all the other pointers. So then you have to copy before you change that one element. And so this is what's called copy on write. It's been in R the whole time, and it's a major aspect of how R works and why we like R. And then once you do need to duplicate, then you duplicate, and you duplicate invisibly to the user. So the user doesn't know, unless you're specifically looking for it, you don't know when it's duplicating and when it's not, and you shouldn't know, and it doesn't matter. But originally, anytime you changed any aspect of an R object, it would duplicate. And then that was painful, particularly for, relevantly to Bioconductor, particularly for S4 objects. That was painful because if you modified one slot, the whole thing, everything else, all of the values of all of the other slots would be duplicated. And so Michael Lawrence, who at the time was not yet on our core, but was on the core development team of Bioconductor, worked with Luke to get shallow duplication in. And what shallow duplication means is you can basically consider certain types of things as separable. So if you have a list, or if you have an S4 object, or a few other types of things, and you modify one piece, only that piece needs to be duplicated. The other pieces don't need to be duplicated. And if you can imagine, or if you have been working on Bioconductor long enough to have been there back in, the pre 3.1 days, this was a major advance, right? Like, especially for a S4 heavy framework like Bioconductor, this was a massive improvement. And the other thing to know here is that for these types of separable objects, modifying the attributes only duplicates the container list, so like it doesn't duplicate all of the elements inside, which is great. Unfortunately, at the time, at 3.1.0, atomic vectors were not separable. Even after this change to put in shallow duplication came in, because of this tight coupling that I talked about before, there was no way to separate the attributes, which live in the header, and how they live in the header is not really important, but they're part of the header, or they're pointed to by the header, and the data. So these were not separable. So if you take a really big vector, like an integer vector, and you assign a new attribute, and you modify an attribute in a way where there are already multiple references to it, so where it would need to copy, then it's going to do a deep copy. It would do a full copy of all the data. And that much like with the S4 case, was both painful and sort of conceptually unnecessary, right? So changing the attributes on a thing doesn't change the values of the payload. It doesn't change, the actual core values of the object. So conceptually, there was no reason that it needed to do this, but technically, implementation-wise, at the time, there was no way to avoid it. And that is a bummer. The other thing is that the elements themselves were not separable either, which means that if you just assign into one value of a 10 million value vector, it has to copy 10 million values, even though, all but one of them stayed exactly the same. Now that ultimately is probably not going to change for a long time, but the attributes thing was something that we were hoping to be able to deal with. Now, none of this is to say that everything was broken, right? Obviously, R was thriving and doing extremely well, before these changes, and certainly before ALTREP came along. But, we were hoping that, with some careful, principled relaxation of some of these constraints, we could actually get around some of these and actually make it sort of backwards compatible, but large incremental improvement to certain aspects of how R is going to behave, in addition to allowing you to do things that you just couldn't really do before. And so there were these limitations, right? So one of the major limitations that's a primary goal for how we do. Sorry, one sec. So one of the major things that we were trying to apologies for that we were trying to get around was this fact that there was no way for there to be sort of non-standard representations of the data. So if you know that you have a sequence, a contiguous sequence, from 1 to 10 million, you don't really need all 10 million values of those to be stored in memory, right? You can actually define that with just 3 values, the start, the end, and the step. And that fully defines every single element within there. And we also wanted to get away from this full duplication upon the modification of the atomic vectors attributes. And one of the major cases of this is actually changing the class of a vector without changing any of the values in it. And the last thing is that there was no way for vectors to sort of know sort of specific things about themselves. For example, whether they're sorted, whether they have NAs and things like that. And if there were a way for vectors to know about themselves, then certain computations would become much, much easier. And so these are the sort of 3 major classes of types of problems that we were going to try to solve with ALTREP. And so the idea of ALTREP is, this is a little bit silly, but it's an alternative way of, making these atomic vectors. Now, the core thing here is that these are still atomic vectors, right? R code and our internals even are not going to know the difference, and that's very important. And we'll talk about how and why that is a little bit more a little later in the talk. But that's a really key point here. And so the design intent is this. We want to generalize the storage of the data payload for atomic vector sets. We want to implement these sort of smart vectors, which are vectors that know things about themselves. We want to decouple data and attributes for these atomic vectors. And this all has to be completely transparent at the R level. And in fact, I don't have this here, and in fact at the C level as well. So what do we mean by generalized data storage? First is the location where the data itself is stored. Where in memory. It doesn't need to be contiguous with the header anymore. It doesn't even need to be in memory at all necessarily. It could potentially be out of core memory. Or it could live in memory, but it could live in memory that's owned by or shared with another process or another object. And the second thing is format. So we can allow for efficient but complete representations of data when the structure is understood and useful, right? So the example of that, which Luke put in as part of the major, the major putting addition of ALTREP in the first place, was these compact integer and real sequences. So anytime you ask R for a sequence, you get an ALTREP that does this thing that I mentioned before, where it models the sequence with those three numbers, the start, the length, and the step, instead of putting them all. So you can immediately get the sequence 1 to 500 million, and that doesn't cost you any memory because we're not allocating memory to store every single one of those values. So next is these smart vectors, right? So these are vectors that know things about themselves. And anytime, the more you know, as we all know, the better off you are. So what types of things can they know about themselves? They can know whether they're sorted or not. And obviously there are algorithms that are much more efficient if you know that data is sorted, not the least of which is sorting. So if you ask a sorted vector to sort itself, it can give you the answer very quickly. Whereas if it's not sorted, then you actually have to do the sort, which is, it's pretty fast in R, but it's still an expensive operation. Lack of NAs is another one. These are the two primary ones that are in there now, but this could be generalized in the future. And this, as I said, makes certain computations very easy, but this is fully compatible with the R internals in that it doesn't, knowing those things doesn't get in the way of just doing the normal thing. So everything about ALTREP is, you can make things easier, you can make things better, but it never gets in the way of the normal way that the internals of R are going to operate on an object. And lastly, we've got this decoupling of the attributes in the data. And so there was no, like I said, there's no conceptual reason that data needed to be copied when there were multiple references and you're modifying an attribute or changing the class of an object. So initially this was a stretch goal, but this was implemented by Luke for a little bit later in 3.6.0 for vectors, only for vectors that are larger than a certain size, because otherwise the overhead doesn't help. But for big vectors, this actually does now happen and has since 3.6. Which is pretty great. And again, the last thing, I keep hammering on this because it's sort of really the core of what ALTREP is, which is R doesn't know. So if you write R code, no R code should ever be aware of what is happening at the level that ALTREP lives. This is just a vector. It has data in it. R can get at the data when it needs to get at the data, and that's it. That's all there is, right? And that's a very important thing about ALTREP. And so as much as everyone, including me, might occasionally be tempted to write R code that is aware of whether something is an ALTREP, we don't want to do that. We just really want these to actually just be R objects and behave as they always would. And yeah, so R code should never know the difference. Normal C code should actually never know the difference either. And we'll talk about how we're able to do that later in this talk. The exception, of course, is hooks that call specific ALTREP methods, which I'll talk a little bit more about later. Those obviously need to know whether something is an ALTREP or not at some point. But largely, if you're just writing R code that's looping over the values in a vector or accessing things or anything like that, that's going to be exactly the same for an ALTREP and a non-ALTREP, because an ALTREP is just a sex. It complies fully with the C API. And so how do we do this? We did this by having ALTREP implement an abstraction that's underneath the traditional C API. And because C code should use the C API and not look underneath it, that means that all the alt-rep stuff is invisible to the C code that you're writing, and to the, as I said, the vast majority of the C internals of R itself. And so this allows us to generalize in the two ways that I talked about, in location and in format, without affecting the internals, without breaking anything that's already in there. And it's going to be compatible with all C code that actually uses this API. So the details, this is a technical developer forum, so we're going to get a little bit into the weeds here. So a couple of details. First, there's a bit in the header that actually indicates whether a sexp is an alt-rep or not. The alt-rep function that is part of the API, I believe, will allow you to check that. Set alt-rep is not provided, and don't ever do that, right? So don't ever poke around in bits of the header, but specifically, definitely don't ever poke around in the alt-rep bit of the header, because if you set it to an alt-rep and it's doesn't have the structure of an alt-rep, like, terrible things are going to happen. And mechanically, alt-reps are essentially a collection of 3 sexps. The first is data 1. This is accessible by these are part of the API. The alt-rep, our alt-rep data 1 and our set alt-rep data 1 functions. And this is usually generally going to be the alternative representation that you're implementing. So for the compact sequences, this is where you carry around the starting value and the length and the step, right? And data 2 has similar accessors, and this is often what I call an expanded version. And we'll talk more about what expanded means later, but basically that means an un-alt-repped version of your alt-rep object, and we'll talk about why you need one of those. But there's a little more sort of variability in terms of what this is, and neither of these are sort of enforced in any way. You have 2 data slots. You have data 1 and data 2. You can do whatever you want with them as long as you do all of the things that an alt-rep class needs to do. But typically, sort of by convention, data 1 is going to be the alternative representation, and data 2 is going to be some sort of expanded version, oftentimes. And then there's the class. So the class contains the method table, which is actually the set of instructions that R is going to use to implement essentially the aspects of the C API that allow normal C code to indicate this. There's an alt-rep inherits methods that is part of the API. There are no other getters and setters for this. You should never be poking around in the class of an alt-rep. But you can check if it inherits from a particular alt-rep class. Currently, these are implemented as constels. I'm not going to spend much time talking about what that is, mostly because this is a technical detail that could change without warning. So you really just need to be using these these sets of API calls to interact with it. But for curiosity's sake, because some of the people here are technical, these are constels right now. So now we're going to talk a little bit about how our internals interact with vectors. So basically the things that alt-reps need to support in order to be fully functional, first-class citizens in the R internals world. It needs to be able to access data, which is this payload that I've been talking about. It needs to modify data in certain aspects. We'll talk a little bit more about that later. It needs to be able to ask the length of the object. It needs to be able to coerce to another type. It needs to be able to duplicate. So if R decides that to preserve this copy on write mechanism, it needs to duplicate a vector. The vector, like you have to have the ability to actually do that duplication, and it has to serialize and unserialize. And those are largely the sort of core pieces. And so what ALTREP classes do is they define methods which support each of these actions. And the methods are the only things that actually interact directly with the internal alternative representation that the ALTREP has. So they sort of receive requests from the C API to do something like access data or, give me the length of the thing or what have you. And they receive that, and then they look inside the ALTREP object to interact with that alternative representation to figure out, what is the length of this thing, or here's the data that you asked for, or what have you. The other thing that all ALTREP classes really should be doing is provide an escape hatch to create a non-ALTREP version, because there are certain rare instances where the internals really actually just need a normal standard text, or they need this sort of contiguous array in memory form of the payload. And your ALTREP class still has to work with those pieces of the R internals. So there has to be this escape hatch that allows you to do that. Or it throws an error. Like it has to say, no, I can't do that. That is just not going to work. I'm going to throw an R level error that tells you that you can't do that with this type of object. And the core here is that ALTREPs, again, just sex, so they need to be able to be passed to all of the R internals. So now we're going to talk a little bit about I don't have time to go through every single method that's in the ALTREP method table, but we're going to talk about some exemplary methods and what they do and how you would implement them. So first, before we move on, like we are way low, near the metal here, right? And so we need to be commensurately careful. So a few guidelines before we move forward is always use the accessor functions. Never poke around at bits that the API doesn't provide access to. The API is largely defined by what is documented in the R writing extension manual. Now there's an unfortunate caveat here, which is the ALTREP stuff hasn't actually been put in the R writing extensions manual yet. But the rule here is that things with start with R underscore ALTREP or R underscore set ALTREP are okay. Anything that doesn't start with that, except for the one thing that accesses the bit and tells you whether something is an ALTREP or not, is not part of the API. So you shouldn't be using it. Always restrict may be shared. I think it might be called maybe reference now. But this is basically this mechanism where you check whether there are more than one reference to an R object. And if there's more than one reference to it, you don't get to modify it in place. You have to duplicate before you modify it to preserve this copy on write pass by value semantic that R has. And that's not enforced for you at the C level. It is at the R level, but at the C level, that's not enforced for you. So it's actually your job. Duplicate if you need to duplicate before modifying data. Also, don't define use R internals. It's called use R internals for a reason. And you can get yourself into trouble if you're doing that. A lot of what this translates to is if R core tells you not to do something in your C code, then just don't do that thing in the C code. And your life will be better, and R core's life will be better, and everything will be good. So now we've got that out of the way. We're going to move on to these. So these are methods. These are specific methods that you will define as you're creating your ALTREP class. It's not the full list again because I don't have time to do that, and there's a lot of duplication there, but there's a few examples. So duplicate must return a sex that is modifiable in the way that our internals are used to being able to modify things. So generally, when you duplicate, you don't get an alt-rep back. You get a normal vector where you can ask for the data pointer and then modify the values of that data pointer, and that will be reflected in the R object. And that is very important because all over the internals there is that assumption that it's going to be able to do that. So no matter what, yes, even you over there in the corner, everybody needs to write duplicate methods to do this, or throw an error. But if you're throwing an error when you're duplicating something, a lot of our code is not going to work. So that's just to not do that. Data pointer. So this is this escape hatch that I was talking about before. So this returns a pointer to the full data in array format, or fails. And the if writable is true, then any modifications that you make to that array must be reflected moving forward in the R object, which basically means that you're not an alt-rep anymore. So this in particular invalidates any metadata that your alt-rep may have had for previously in terms of knowing that it was sorted or knowing it was in NA. All of that must mandatorily be dropped as soon as a writable pointer has been accessed. You just duplicate into a standard vector and carry that around and use that from then on once this has happened. Next, we've got data pointer or null. This is basically translates to do data pointer if that's okay with you, but you can say no. By you, I mean your alt-rep. So if you're an alt-rep and you don't have easy access to an already constructed sort of array representation, then you can return null, and the code that's calling this will be like, okay, you didn't want to do that, I'll go do something else. But if you do already have that array, or if you want to make it for some reason, then you can return that, and that will sort of allow the code that's calling it to be efficient. So typically, after data pointer has ever been called with writable equals true, any time after that, data pointer or null should already have that array around, so it should be able to return that. Then you can return null, or you can return this array. So this, in particular, should never throw an error, except potentially, I suppose, like a memory error or something like that. But because this is allowed to say no, you should just say no if you're ever not able to create the vector, the array. And so anything that you return that's not null should be and must be the full data in this array format. Next is ELT. So this is element. So this simply returns the value, not a pointer, but the value of a single element of the vector. So this is not destructive to your alt-rep because you're returning a value, so there's no modification that could ever happen. So this preserves all your metadata, it preserves your alternative representation and all of that. Next, we're going to talk about sortedness. So a little bit of an aside. So sortedness in alt-rep is modeled by this enum that I have here. This is in the rinternals.h header, but it's not. It's part of the public bit. It's not part of the private part. And this is all of the different values of sortedness that your alt-rep can say that it has. So you've got sorted decreasing with NAs first. You've got sorted decreasing with NAs last, which is the default. You've got unknown sortedness, which is NA. You've got sorted increasing. You've got sorted increasing NA first, and then you've got known unsorted. And these are the only values that your isSorted method should ever return. So this is sorted, just returns one of those values based on what your alt-rep knows about itself. So if your alt-rep doesn't know anything about itself, then it can just return unknown sortedness. You must always return unknown sortedness if a writable data pointer to your thing has ever been retrieved. And again, so we need to be very careful, and I'll drive this point home a little bit more even in a little bit. But known unsortedness, you can only do that if your vector has more than 3 or more. That actually should be 3 or more, not more than 3. But 3 or more distinct values, because if you only have 2 values, it is sorted in one direction or the other. You're guaranteed that, right? And so it should never, ever, ever be known unsorted unless it has 3 distinct values. And sorry for the typo there, but and is not sorted in either direction. Okay. So creating an ALTREP class, I apologize, the code goes off the rails a little bit there, but you create this C function. You create the ALTREP class by in this case altReal makes the real vector version. Alt integer right here would be an integer version, etc. And then you call these setters, these method setters, and you pass it the class, and then you pass it your method that you have written for that particular method. And so you just call these, and then you're done. And then R will know about that ALTREP class. And then you have to write an actual constructor, which I don't have a slide for, which actually constructs an object of your ALTREP class. And there's an example of that in the package that I have. There's a link later, but it's in the Slack. Okay, so some guidelines for writing ALTREPs. It's very important that you're extremely careful and conservative. So metadata in particular must be right absolutely 100% of the time, because the R internals are going to assume that the answer that it gets when it asks the vector if it's sorted or not is always correct. And so that means that it needs to always be correct, or else R at best will give incorrect answers, and at worst could cause larger problems. You should use the API even in the code where you're implementing your ALTREP methods. That should still only hit the API. Many methods which return sexps can return null to decline to do something. There are a couple of exceptions. Duplicate doesn't. Actually, duplicate might or might not be able to do that. I would need to double check that. But many of these can do that. And you should if you're declining to do something. So don't re-implement something if there's no benefit to the alternativeness. Just let the existing code deal with it. Another thing is be very wary of violating pass-by-value mechanics. You can do it. Like, you're down in C code, nothing can stop you from doing it, but usually don't. There are a few exceptions to this, but be very wary and very careful. In particular, you can do things like marking things as non-mutable to share things in a read-only way, where with a single copy in memory. And so as long as you're able to get away with having read-only things, you can just mark things as immutable, and then you can still share, you can still not copy anything around, but you don't need to to actually violate those semantics. A few more specifics. Basically, ignore the _ex variants. This is I was talking with Luke, and this is what Luke said you should do. Just use the defaults for the ex methods. So there's a duplicate _ex, and then there's a unserialize, I think, _ex. And just let the defaults do the work for that. Don't worry about that. And it's going, both of those cases, they call down to duplicate and unserialize the non-EX versions. So you just write those and just let the EX versions do their thing. And I'm gonna iterate this again because it's important. Your duplicate method must return a sex that can be modified via direct interaction with the writable data pointer once it's been retrieved, because that is how certain parts of the internals are going to behave or fail by throwing an error. And the other things you should write functions or macros that abstract the details of what's in data 1 and data 2. And then even in your own methods, you should use those. And this is just for your own sanity to sort of make your code cleaner. So all of the examples in the GitHub repository that I will link to all are doing stuff like this. And all of the examples internally, if you go into source main altrep classes.c, in the R source code itself. Those are all of the sort of internal to R altrep classes. That's where they all live. And you'll see that this behavior there as well. Generally, don't write C code that is mucking around with the internals of an altrep object outside of the methods for the class that altrep is. Because that's just, you're gonna get into like a nightmarescape if you're doing that. Okay, so next is, so we've talked about what the altrep is doing. So what is the R side of things doing? So, and how should you write R or C code? Sorry, our internal side. So the C code that can use these altreps in the way that is best for them. So the primary thing that C code is going to do with an altrep is get data from it and get the length. There are a few other things, but that's the biggest one by far. So I'm just going to go through that aspect of the C API with the integer cases as an example. There are real underscore versions and raw and logical and all of those as well. So the integer. This gives you, this is the data pointer thing. This gives you a writable data pointer. This must always succeed or throw an error, memory error, regardless of altrepness. You've got integer 0, which you should generally not call directly. But this basically assumes that the thing that it's given is not an altrep, and then does the old version. It's slightly faster, but it's not that much faster, and you should generally not be calling it. Integer underscore RO, that's an O, not a 0 like the one above it. This gives you a constant pointer. And the thing about getting a constant pointer is that it's not modifiable, which means it doesn't destroy the altrepness. It doesn't destroy the metadata that your altrep knows about itself. So when you can, if you need a full vector, a full data pointer, but it's okay for it to be read-only, you should call this version instead of the writable version. And then integer or null, this calls data pointer or null, which we talked about already. And again, I'm hammering on this over and over, but modifications in the addressed memory of the pointer that you get when you call integer must be reflected in the R object. This can't be detected by your altrep class, which means that the metadata and representation are going to be invalidated. And often the way that I write many altrep classes is you'd use data2 to just store a standard vector version after that's happened, and then just always delegate to that. So you'll see that in the code that I posted. But when you can, you should call integer RO or integer or null if you need the full pointer, if you need the full data all at the same time. But the thing is, you usually don't actually need the full data all at the same time, which means that there are these alternatives, which is, so you can call integer underscore ELT, which will return the value for a single element. And that can be painfully slow inside of a tight loop, though. So what you actually often want to do is this integer get region. So what this does is this populates a buffer with the values from a contiguous region without copying the whole thing. So it only copies the values of that particular region. And because they're copies, it's not destructive to your altrep or to the data that's there. Yeah, so how not to do it: avoid getting writable data pointers whenever you can. Sometimes you need it. The vast majority of times you don't. When you don't need one, don't get one. Integer ELT is painfully slow in a tight loop. But Luke added a thing as part of ALTREP, the ALTREP framework, that allows you to sort of use get region without having to think very much about get region. And that's this iterate by region macro, which is inside this include our extensions iter macros.h file. So what this does is it chunks up your data, your vector, into pieces, does get region on each of those pieces in sequence, and then applies whatever code you want to that one chunk, that pointer. And it does grab the whole pointer if the altrep will give you the whole pointer, but then if not, it does that. And so wraps repeated get region calls. It's safe. It's altrep safe. It doesn't destroy altrepness or metadata, and it allows for efficient tight loops over pointer access, which is something that you want to get your code to go fast. There's a 0 version, which assumes without checking that it will not be able to get the full data and always does the chunking. Generally, you don't need to do that. Generally, you should call the non-zero version, just like elsewhere. And then there's a partial version where you can specify the start, where you want this access to start and how many you need. So here's an example. This is the code for which. This is internal code for the which function. So what you can see here, so we've got this buffer that we're going to populate with the answers, which is the indices for which the logical vector is true. The logical vector is v here. So we're going to iterate by region across v. The name of the variable is going to be pointer. IDX, actually, we don't need to worry too much about. NB is the number in the current buffer. So it's the number of observations in the current buffer. By default, that's going to be 256, or however many are left, whichever is smaller. Integer is the C type. Logical is the sort of macro type, so logical or integer or real. And then we have our code. So this is the set of code that will be run across each of these chunks that are 256 elements long. So we loop. We have a tight loop, and we say if the pointer is true, so this is the pointer to the data in our logical vector. If that is equal to true, we put the offset, we put the buffer to be the offset plus I, and then we, at the end of that chunk, we increment the offset to be the start of the next chunk, and that's it. And that is an altrep safe tight loop. So you'll see that if you look around at various places in the R internals. And this is also what your code should roughly look like when you're doing a tight loop across values of things. Okay, so here is this link. This is also one of the repos under this organization is in the Slack. that you can click on. And that's where Luke and I have written some sort of illustratory examples of packages that implement ALTREP classes. And finally, for acknowledgements, I'd like to acknowledge Luke, who's worked closely with me and was willing to do a lot of the work on the R side in terms of implementation, and has been patient with me as I've, worked on this with him. Also, Michael Lawrence, who was my manager at Genentech when a lot of this was conceived and was very supportive of me doing this and contributing to R, which I'm extremely grateful for. And Thomas Calabera has also been part of the R the discussions in terms of adding this. And also thank you to Mike Smith and the Bioconductor Develop Forum for the invitation, and finally to all of you for listening. And so with that, I think we have about 12 minutes, so I can either give a very brief overview of this code that I wrote, or I think we'll start with any questions or comments that people have.
Thanks, Gabe. That was awesome. I think we should take some questions. I think there's a few in the chat and things. So, Henrik, if you're still on the line, you can go first, and then we'll see where we go from there.
Can you hear me?
Yeah.
That's good.
Okay, awesome. Oh yeah, I got so many questions. But let's start with one I can imagine people who have native code now C code that the first thing you might want to look into is, like, I can take my matrix stats example. I had it on my to-do list for a long time. So checking for missing values in doubles is very expensive. Yeah. So I would like to query the double matrix coming in or the integer matrix coming in, whether there are NAs or not.
Yeah.
Can you show that, how to do that? Blaine, is it just like...
It's that.
That's all I need to do. Okay.
Yep.
That's brilliant. And if I then scan, so the answer is in the chat there if anyone wonders. And if I want to then say, if it's saying unknown, and then I go ahead and scan for NAs myself, can I then update that object and saying
No, so you can't update it. We had discussions about that, whether we could in place update, and that may eventually happen in for example is.na. But currently no. Currently there's no way to update metadata for an alt-rep from outside of the methods.
So who is allowed to do that then?
The alt-rep methods can do it. So if your alt-rep method sees something happening where the value of those should change, then it can do that. But currently, the way it's currently defined, there are accessors, but there are getters, but no setters for alt-rep metadata. And this is something we've considered, but Luke, I think, ultimately decided that for now, at least, that's not going to be something that's supported.
Okay, I can understand.
It may be in the future, but right now it's not.
Yep. Thanks for that. I have plenty more questions, but if someone else want to pop in here.
Hey guys. So thanks Gabriel for the great tutorial.
Yep.
So I have a few questions, and the first one is that I'm not sure if I understand the data pointer part correctly. Like when the data point function is called with readable equals to true, and why we must mark the sortedness as unknown. So why can't we recompute the sortedness when the isSorted function is called?
So I mean, you could, but so the contract for is sorted is that it's supposed to be extremely fast, right? It's not supposed to actually do computations. It's supposed to just be a lookup. And so it's going to be called in places that are going to assume that that's not expensive to do. Like it's called in sort, right? And so ultimately what you're describing, you would be sorting things twice, essentially, because you would call it as unsorted to check whether you need to sort or not, but then that would actually do a check for, so you wouldn't be sorting, but you'd have to do unsortedness checking, and then you would sort, right? Or is unsorted is another example where that would actually be run like twice. Well, actually, you could, in that case, you could return known unsortedness, so you might be able to get away with it. But the basic answer is these are assumed to be very fast, right? These metadata retrievals, and so you may get unexpected slowdowns if you're actually doing heavy computations inside them. I suppose from a technical standpoint, nothing would stop you from doing that other than that basically.
Okay, thank you.
Luke, do you have anything further on that?
No, that sounds good.
So I have a related question. So I see you mentioned about the setter function in your slides, but it seems like the setter function is only valid for the character vector type, and there's no setter for the numeric vector. So that is it. That will I add these setter functions in future, or there's some reason that we cannot do such things?
Yeah, so the setter function is another one of those things where we went back and forth, but ultimately I deferred to Luke, who both, is the more senior person and the person that has to maintain it because he's the one actually in our core. And right now, basically, it was decided that to do the conservative thing, which is you can't poke into an ALTREP because then you have to say, okay, is your method actually updating sortedness correctly when you set things? And if you set for an NA, is your method catching that, right? Because again, there are places in the R internals that assume, like hard assumptions, that the metadata that they're going to get is correct. And it would be very, very easy to write an ALTREP that had a setter where that was no longer the case, right? And so then you're running around where these bugs and packages can actually make the mean function give the wrong answer, right? Which is bad, right? You don't want that. So I think that's why. But Luke, I mean, again, ultimately I was pro that, but I deferred to Luke in terms of being more conservative and safer to that. So
thank you. So I have one last question. So so I see from Martin post in the chat. So for the vector x, you cannot do you cannot apply. You can only read the data from x, but you cannot apply any math functions on the object x, on the ALTREP object actually. So that will I have any plan for adding the support for general support for the general operations on the ALTREP object?
So this is are you talking about the error memory exhausted thing?
And actually, we can take the log of x as an example.
Right. So the thing about log of x is that it is, so if x is a sequence, of length, a trillion or something like that, right? Some ridiculously long length, which again in memory is still only going to be 3 values currently, because of the ALTREP, because we have that structure where we know it's a sequence, but log of x isn't a sequence anymore, right? Like it's a sequence in log space, but it's not a sequence in non-log space, right?
Yeah.
So you would have to so you could write an ALTREP that put things into log space, right?
Yes.
Like sort of is a delayed thing. You could do one. I don't know of any plans to do that right now, but that would be how you would have to do it, right? Like, because log takes the values and then it logs them, right? And so the log of a sequence is no longer modelable as the same type of ALTREP as this sort of sequence ALTREP, because they're logs now, right? They're not steps by one anymore, right? And so there are things that you could do, like what I just described, and there are but ultimately, yeah, you would need, and like then you're sort of whack-a-mole combinatorial explosion type of situation where you'd have to write one for every single one, and you just sort of don't do that. I would also question why you need a trillion logged values at the same time, right? Maybe you don't need those, in which case you could just not do that. But yeah, it is. There are some things that are not supported that could be. I see Martin is mentioning var, which could, as far as I know, be using iterate by region, but isn't yet, just because we haven't changed it to do that yet. But those types of things will, over the course of the future, more and more things will support it where they can. But things like taking the log of an enormous sequence, you could write something that actually did that in a package if you wanted to. You could implement this log sequence of logs, ALTREP, and give a method for log that did that instead. I wouldn't want to promise that that's going to go into the R internals, mostly because I don't actually decide at all what goes into the R internals, right? Because I'm not on the R core team. But even if I were, I would be a little skeptical that would be worth doing. But other things like this var thing, I think, will get fixed as things move on.
Okay, thanks for the insight for the ALTREP.
Yeah, I mean, it is possible to do, in principle, to do a number of deferred evaluation kind of things. For example, if you're writing a code to do a log likelihood and you do the computations on the vector and then sum it up, it would in principle be possible to push that into something like an ALTREP so that you never actually generate the full data. But I don't see, and you have to be very careful of what we're putting into base R in terms of how complex it gets, and tuning that sort of thing is there's only one place right now where we do something where we do X if the value is small and Y if it's different, and yes, it's a little more efficient, but it's a pain remembering where that threshold is when you're debugging stuff. So you just really have to balance the maintainability of things. But there's certainly room for people to experiment with this kind of stuff if they want to.
Yeah, I understand it. I feel like just some ALTREP package that is designed for the big data, and with the big data, like you can only read the data, but you cannot really to apply any operations on the object. Like you want to do a log transformation, that is impossible for large data. So I feel that can be a very exciting feature if it is supported by the ALTREP.
I mean, and like I said, in a package like that, you could, for your representation of big data, you could write something like that, right? But that would be different than having the R internals do it automatically for you.
Yeah,
right?
yes. Yeah, that's all my question. Yeah. Thanks, Gabriel, for answering my questions.
I got another question, two questions that are very related, and I'm going to ask them as examples. So could you use ALTREP to basically define a constant in R, so you can't reassign it later?
I mean,
and the follow-up question is like what I'm really interested in. Could you prevent a coercion? So if you like create an integer vector and then you assign a double, it will throw an error rather than coercing everything to double.
I mean, coerce is a method that your ALTREP gets to set. So in principle, you could throw an error in that method. Now, in terms of how much of sort of normal R behavior that would break, I would not be comfortable like giving a number on that without thinking about it a bunch. But you could make that happen. Whether R would still ultimately be functional for you or not is a little less clear.
Okay.
I don't know, Luke, do you have thoughts on that?
I don't think it makes much sense. And it's the way R works. And if you create one of these things, you add 0L to it, that thing you can coerce again, but it's identical. And I don't think I'd want to go there. You could certainly create an ALTREP that throws an error when you coerce. I don't think you're going to be happy with the result. That's my guess.
But I will try. See, I'm thinking about my internal code and conservative things, because you spot expensive coercion by mistake, which creates lots of copies. So be able to like catch those.
Which is something that Luke has put in and was one of the sort of core initial ones. You can defer coercions. And then if they never ultimately end up being needed, you just don't do them. And then the expense is never realized, right? Like, so there's is it I can never remember if it's the row names or the row names of the model frame in a big LM, which is just a character vector, but it's a character vector with like 1 through whatever number. And for big things, that was really expensive and useless because no one ever looked at it anyway. And so that's deferred now, thanks to work that Luke did as part of the initial push. So you can do things like that, where you pretend that something is coerced, but if it doesn't actually ever matter, then it doesn't get coerced ultimately in the end. Or if it were coerced back, then it would round trip without changing. So those might be better ways to knock down this sort of unneeded or unwanted coercion cost rather than trying to model constants.
Yep. I mean, the constancy was just a basic example coercion. Another one is like preserving length of a vector, then prevent the expansion by mistake, for instance. That's right. But so you're saying these things can be done in ALTREP if I would like to play around with it.
So the constant thing could potentially, like, you can write an ALTREP that refuses to be coerced, but as Luke said, it may or may not do what you ultimately are wanting it to do, because you probably don't want all your code to actually error when that happens, You want it to just not coerce. I mean, maybe in terms of debugging, you do actually want it to error, but in actual production code, you probably wouldn't want that. You would probably actually want it to behave itself. But yeah, I mean, it might be there might be sort of alt-rep like debug tooling that where if you really don't want these things to be coerced, you temporarily use these alt-reps that throw errors when you coerce, but then you don't in your actual code do that. You just do that to detect coercions. That might be useful.
Yep. That's how I'm thinking. Yeah. Thank you. This is brilliant work you guys done. Okay.
So I'm just going to jump in because we're over the hour mark. So I just want to say thank you to everybody that's come along, and I've really enjoyed it. It's been really great. But I don't want to stop the discussion. I just want to thank people that have to run off to other meetings and things. So then I just want to point out there is another question in the chat about whether alt-rep was inspired by other languages, and if so, which ones?
Yeah, so so from my side of things, I can't speak for Luke, but for my side of things in terms of the proposal, it was less inspired by other languages per se, and more inspired by actually, things like Bioconductor, which they use the sort of R-level generic process to sort of abstract things like that, which is not to say that there are not other languages that do things like this. I'm not claiming that R is the first, but in my mind, I was thinking in terms of sort of methods and abstraction, in terms of basically making S4 objects that could be passed to the R internals and work. Something sort of akin to that is what I was coming from. But Luke may have more insight on relationships to other languages, and because he did most of the actual implementation.
Yeah, when I first designed it, it's not really a language feature as such. It's an internals feature, and it's more a matter of we've got this big body of code. How can we make some changes without breaking everything? And so in that sense, it was very R specific. I suspect many other language implementations have faced something similar, but it's not something specific to a language. I did not see anything when I started on it that was like it. It was more, I was thinking in terms of the two specific examples was the compact sequences and the avoiding that. I tried some other things to avoid those crazy as-dot characters on huge, long, unused index vectors, and I think those were the main motivating things to figure out how can we make that happen and build on it. But it's really an implementation thing, not a language thing as such. If we were redesigning R, we'd probably design it in such a way that you didn't need this, but we're not doing that.
Yeah, and that related to that, that's why, like, at numerous points in the talk, I sort of stressed that, like, the goal of this was that our code doesn't know the difference and our internals don't know the difference, right? Like, that was a major design constraint, right? Because I knew, like, when I was proposing it, if that weren't the case, like, the proposal would not be able to be accepted, regardless of how good an idea it might be in the abstract, right? It had to not break code that existed already. And so really, that's why we're underneath the C API, even though, people may or may not like the C API, but it's there and it's what's used. And so we had to go underneath that in order to be safe with the code that existed already. Were there any more questions?
How much of a maintenance burden has it put on, I guess, on you, Luke, for like, how much did you change and do you regret making these changes? Or are you pleased enough with the result, I guess, that it's been worthwhile?
You probably have to ask the other ARCOR members how much they're unhappy with having to deal with it. On the whole, I think it's worked out. You know, we didn't break too many things, and yeah, I mean, there's things we wish you could do, but we don't go there because it might break stuff, and we'll probably slowly move forward. Right now, I think we need to focus more on let's get some documentation written up on this and continue to harden everything. But I'm very happy with it on the whole that we did it.
Do you have a sense how much more of the core R code can add ALTREP to that? I mean, are you like done with updating the base R code?
I mean, that's the kind of thing where if somebody wants to think about doing a patch, I'd look at the patch rather than try and do it myself. In many respects, that aspect of this paralleled what we did a few years earlier with long vector support, where we tried to design it so that we can get it in a few places that haven't been modified yet. We'll just throw over the error. There's still places where that could be augmented, and I think it's going to be similar with ALTREP as people look at, hey, that thing probably should be made ALTREP aware, and yeah, if you really care about it, send me a patch. Is probably going to be the answer. Or if I decide I care about it, I might do it, or Gabe might send one in. So.
Yeah. So I mean, I can say that that I have done that in a number of places, right? So like which is the one that I showed in the slides, was originally not, and then I changed that. The motivation for that was actually if else, I think, which uses which internally, but by getting which, we actually got both of those to be sort of alt-rep preserving. And there's a few other places. A lot of times this is the type of patch that's actually pretty straightforward to write. So you find anywhere where it's the, grab a data pointer, tight loop, do something with the data pointer, and you convert that to an iterate by region, and you're done. And then it sort of is okay with alt-repness. And so, I may actually even write something up to that effect at some point in terms of, but like I've submitted a number of patches that were converting tight loops to iterate by region tight loops, and usually that's all it takes. And so, like I said, the var one I haven't done yet, but I am fairly certain that could be converted. And if someone else doesn't get to it first, I will eventually get to submitting a patch for that, and things like that. So, but other people can too, if they're interested in contributing. You can look at patches that I've done, and again, I'll try to write like a blog post or something about it. But for that particular type of adding alt-rep support, it's actually quite straightforward. Adding a new ALTREP class is something much more involved, and something that would need to involve a person from our core much more closely and much earlier, I think. But in terms of just support, making it support existing ones, it's actually pretty straightforward to do.
I can imagine like you have to think about testing and test coverage of all those different branching you're adding.
Yeah. One of the things that I typically do, is there are ways to force an alt-rep to be not an alt-rep anymore. The largest one of which is to assign a value into one of the elements of it, right? Because we don't have those setters. And again, as I mentioned numerous times in the slides, that destroys alt-repness essentially. So if you do that, and then compare the outputs with the one that you did that to and the one that you didn't do that to, and they're the same across all of the different possibilities of sort of input class and input type and all that, then you're generally going to be in pretty good shape. And so you want to be running those tests to make sure that that is happening. And then it's just sort of being clever about thinking about the corner cases and making sure that you have the proper breadth of that type of test. But that's basically what you ultimately do.
So are there any more questions? If not, I will thank both Gabe and Luke again for attending. It was a really awesome deep dive into some of the internals of R. We cover quite a breadth of things in these sessions, but I think this was the lowest down in the stack, way below. I liked your Here Be Dragons slide. I even wrote I had a comment on that before you threw the slide up. I'd already written that next to one of my notes where you said, do not ever touch this bit. So I really enjoyed the session. I hope everybody else did. Thanks again for presenting. For those who are thinking about next month's, at the moment, the date clashes with the European Bioconductor meeting, which is obviously online. It's not really in Europe. It's free. Sign up if you haven't already. But we might end up moving the date of this particular meeting because we'll be zoomed out by that point. So thanks again, guys. And I will see people in approximately a month's time for this meeting. Cheers.
Thanks for watching.